Assalamualaikum. Can you hear me?
Pak Sony, disambut Pak, ditanya itu, can you hear me?
Yeah, I can
Oh
hear
yes,
you.
yes Prof, we can hear you.
Okay, all right. Thank you.
Okay, but Professor?
Yeah.
Okay, you can hear my voice.
Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Masya Allah. Are you in office right now? Okay, we'll start several minutes. In several minutes. Pak Heri.
Dr. Sony, can you hear me?
Yes.
Okay.
Okay, clear.
So, should I start now?
Yeah, we're waiting for the opening ceremony.
All right. Yeah. Sure.
Okay, good morning, Prof.
Good morning.
Assalamualaikum.
Waalaikumsalam.
Okay, we are waiting for the dean for several minutes.
All right.
Thank you.
Halo, good morning. Assalamualaikum, Profesor
Good
Dr.
morning. Good
Ekram
morning.
Muhammad.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, nice to meet you this morning, and
Nice to
I'm
meet you.
ready to uh, join with our program and maybe the committee we are start now. Yes.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning. Shalom. Om Swastiastu. Nama budaya. Salam kebajikan. Tabi pun. Honorable the Dean of Faculty of Mathematics and Natural Sciences, University of Lampung, Dr. Engineering Heri Satria, MSc. Honorable the Chairman of Department of Chemistry, Faculty of Mathematics and Natural Sciences, University of Lampung, Dr. Mita Rilianti, SSI, MSc. Honorable Head of the Chemistry Master Study Program, Dr. Ilim, MS. Honorable the Speaker, Professor Dr. Ikram Mahmud. Honorable all the lecturers and all the participants. Good morning, ladies and gentlemen. It is an awesome and precious chance for us to be a master of ceremony in this morning on Wednesday, 11th of September 2024, in our event, General Lecturer, Smart Materials, A Way Forward. Let's be thankful to Allah Subhanahu wa Ta'ala who has given us mercy and blessing so that we could gather here to join a wonderful event, General Lecturer, without any obstacles. Hopefully, this event will run well till the end. Peace and salutation we devote to the Prophet Muhammad SAW, and we all do hope can get his intercession on the day of the judgment. Amin, amin, ya rabbal alamin. Ladies and gentlemen, in this nice morning, let's begin this opening ceremony by saying Basmalah.
Bismillahirrahmanirrahim.
The next agenda is singing the national anthem of Indonesia Raya and Hymne Unila. To Army, time is yours. Thank you for Army. The next agenda is delivering speech. Now, we will invite the Dean of Faculty of Mathematics and Natural Sciences, University of Lampung, to deliver a welcome speech. And with high gratitude, we would like to have Dr. Engineering Heri Satria MSc to officially open general lecture. So Dr. Engineering Heri Satria MSc, time is yours.
Thank you, Anur Valita Sari, for the timing. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Warahmatullahi
Firstly, the Honorable, the speaker, Professor Habibun Nabi Muhammad Ekramul Mahmud. Welcome to our faculty and also our university, Faculty of Mathematics and Natural Sciences, University of Lampung, onlinely. Hopefully, sometime you can visit us directly. So offlinely, we can meet directly here in Lampung Province, Indonesia. First of all, I'm proud to open our event this morning, general lecture that conducting with Magister of Chemistry, Faculty of Mathematics and Natural Sciences, University of Lampung, as a part of academic activity of our faculty activity this semester in second semester academic 2023 and 2024. This event is a part of our academic activity that every study program should be conducting the similar event, and then this event have a topic with the smart material way forward that we have the honorable speaker from University of Malaya will explain about smart material, the prospect of conducting polymer, and then we ready to follow the explanation this morning. Before the explanation, I would like to introduce our faculty. Our faculty has already established since 1989, and then until now we have already 35 years old. Serve the education in Lampung Province, Indonesia. And then also until now we have 5 departments with 14 program study that serve the education from the diploma to the doctor. So we have one program for diploma, and then we have 5 program for magister and 1 program for doctor, and then the maybe about 8 program for the bachelor. For the magister especially, we have biology and chemistry, mathematics, physics, and also computer sciences. And then we have a special program for doctor, namely Dr. MIPA is already established since 2011 and is already produced the graduate student around 22 doctor from our faculty. So for all of the activity, we would like to collaborate with many university and also many faculty from many university in the world, and Malaysia is one of our collaborate country that because we have many similarity, including the uh, including of the academic atmosphere. So with University of Malaya, we have already at least have many collaboration since our department, one of our department, it is the chemistry department, starting to be international accredited by Royal Society of Chemistry. So from Alhamdulillah, until now, the department has already accredited internationally, and then also University of Malaya help us a lot to realize that program. So thank you very much. So also, I would like to give my high appreciation to Professor Habibun Nabi Muhammad Ekramul Mahmud PhD to be a speaker to follow the explanation and also to discuss actively. So I think it is around 15 people join with this program this morning, and then also will increase maybe until this ceremony open agenda. So thank you very much once again, and then for all of participants, have a nice time to increase our collaboration, our knowledge this morning, and hopefully Professor Habibun Nabi Muhammad Ekramul Mahmud will also give the lecturer for the future time. Thank you so much, and then we'd say Basmalah, Bismillahirrahmanirrahim. This lecture I open officially. Bismillahirrahmanirrahim. Thank you very much for all of the audience, for all of the audience attention, and then I would like to finish my speech with saying wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you so much, Dr. Engineering Heri Satria MSE, for delivering and opening this general lecture. The next agenda is prayer, who will be led by Mr. Saiful Bahri MSE. So Mr. Saiful Bahri MSE, time is yours.
Thank you very much for Master of Ceremony. And can you hear my voice?
Yes.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Ladies and gentlemen, allow me to lead prayer in an Islamic way. Ladies and gentlemen, please be pleased to adjust according to your respective beliefs. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم حمدا شاكرا حمدا ناعما حمدا يوافي نعمه ويكافئ مزيده يا ربنا لك الحمد كما ينبغي لجلال وجهك الكريم وعظيم سلطانك يا Allah, our Lord, all praise to be to you, the preserver of the universe. All praise for your gifts and pleasures that you bestow on us. Praise be to your majesty. All praise to your glory and power. Allahumma salli wa sallim ala sayyidina Muhammadin wa ala alihi wa sahbihi ajma'in. Ashhadu an la ilaha illallah wa ashhadu anna Muhammadan Rasulullah. Ya Malik, Ya Quddus, we glorify your name because only you, our Lord, only you, only to you we prostrate, only to you we give thanks, and only to you we pray. Ya Rahman, Ya Rahim. Only to you we worship, and only to you we ask for help. Ya Allah, today we gathered here for a general lecture in order to Chemistry Master Program, Faculty of Mathematics and Natural Sciences, University of Lampung 2024, discussing smart materials, a way forward. Therefore, Ya Allah, launch our event. Bless you. Fill this meeting with kindness from beginning to the end. Open our minds, flex our tongues, and give us bright ideas to build the scientific and economic strength of our nation. Ya Allah, who knows the unseen, guide us with your guidance. Bless us always with your destiny and make our hearts always happy with your gifts. Rabbi israh li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Oh my Lord, open my chest and smooth my tongues and make my affairs easy. Allahumma arinal haqqa haqqan warzuqna ittiba'ah wa arinal batila batila warzuqna ijtinabah. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzaban nar. Subhana rabbika rabbil izzati amma yasifun wa salamun alal mursalin walhamdulillahi rabbil alamin. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Saiful Bahri, MSc. The next agenda is delivery of material and discussion. The discussion will be led by moderator. The moderator is Dr. Soni Widyarto, MSc. I will read the curriculum vitae of Dr. Soni Widyarto, MSc. Name: Dr. Soni Widyarto, SSC, MSc. Email: sony@fmipa.unila.ac.id. Place and date of birth: Jakarta, October the 30th, 1971. Dr. Soni Widyarto is a lecturer at the University of Lampung, specializing in several fields of chemistry. His expertise is reflected in the courses he teaches, which include analytical chemistry, separation technique, quality control in chemical analysis, environmental chemistry, statistic cheomatics, research methodology. Additional background: Bachelor degree, Chemistry, Universitas Gadjah Mada. Master degree, Polymer Chemistry, University Putra Malaysia. Doctoral degree, Polymer Chemistry, Institut Teknologi Bandung. Research experience: 2022, Water Quality Assessment using Water Quality Index. 2021, application of diffusive solid phase extraction method based on magnetized cassava peels. 2022, eugenol crosslink with 10% diphenyl benzene as a carrier in the polymer inclusion membrane method. Scientific publication: Study of electrolytical column conductivity. International Journal of Applied Electromagnetics and Mechanics. 2023. Study on activated carbon derived from cassava peels. Research Journal of Chemistry and Environment 2023. Conference presentation. Presenter at the International Conference on Advanced Material for a Better Future 2016. Certifications. Competency Assessor Certificate, August 2022. Determining Acceptance Criteria and Intermediate Equipment Checks 2022. Dr. Soni Widyarto extensive academic, research, and professional background demonstrates his dedication to advancing the field of chemistry and educating future professionals in both theoretical and practical aspects. To Dr. Soni Widyarto, MSc, time is yours.
Thank you. Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, a very warm welcome to all of you We are truly delighted to have you with us today. Your presence, whether offline or online, is highly appreciated and vital to success of this event. We want to sincerely thank you for taking the time out of your busy schedules to participate. We hope this session will be insightful and beneficial for all of you. First and foremost, I would like to extend our deepest gratitude to our distinguished keynote speaker, Professor Dr. Ikram Mahmud. Thank you, Professor, for taking the time of your busy schedule to share your expertise and knowledge with us. It is truly an honor to have someone of your caliber with us today. I would also like to express our heartfelt thanks to all the participants who have joined us from various locations. Your presence is a testament of your commitment and learning and professional growth. We hope that today's session will provide you with valuable insight and practical knowledge that you can apply in your respective fields. Before we move on the presentation from our guest speaker, I would like to take a moment to introduce him by reading a brief biography. This will give us a better understanding of his impressive background and expertise. Professor Dr. Habibun Nabi Muhammad Ikramul Mahmud, PhD, is currently serving as a professor in the Department of Chemistry at University Malaya, Malaysia. He has spent about 13 years, having joined the department as a senior lecturer in 2011. Professor Ikram academic journey is marked by notable achievement. He obtained his BSc and MSc in Applied Chemistry and Chemical Technology from the University of Dhaka, Bangladesh in 1986 and 1987 respectively. Continuing his pursuit excellence, he earned Master Engineering in Chemical Engineering from University Technology Malaysia in 1998, followed by a PhD from University Putra Malaysia in 2006. His research interests, Professor Ikram is focused on two key areas: the synthesis and characterization of conducting polymer for a variety of applications, the catalytic conversion of biomass into energy, exploring sustainable solutions for the future. Throughout his academic career, Professor Ikram has been a dedicated mentor. He has supervised 11 PhD students and 6 master students, guiding them to their research journeys. Additionally, he has served as an examiner for more than 35 PhD and master's theses. Professor Ikram has contributed significantly to the academic community. He has published more than 60 peer-reviewed papers in both international and national journals. His scholarly work extends to numerous international conference papers. Beyond his own research, he has been a valued reviewer for several international journals. As a principal investigator, Professor Ikram has led 7 research projects. His excellence in research has been recognized with 12 research awards from national and international research competition. That was a brief biography of Prof. Ikram, who is truly remarkable. Ladies and gentlemen, we have an exciting agenda lineup, and I am confident that the discussion and presentation will be both informative and inspiring. I encourage you all to actively participate, ask questions, and engage with the content and our speaker. Once again, thank you for being here. Without further ado, let us commence our webinar and give the floor to our esteemed speaker, Professor Dr. Ikramul Mahmud. Thank you.
Assalamu alaikum and very good morning.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Respected Dr. Engineer Heri Satrian, the Dean of Faculty of Science and the departmental head, Professor Mita Rilawanti. Okay. All right. It's my privilege to be here with you I'm really honored to be here in this Lampung University. I heard the name of this university before the time our departmental head, Dr. Kartini, and her team went to Lampung University some time ago. And with this connection, actually, we can have a lot of collaboration, a lot of discussion, in fact, can be done in order to make some collaborative effort fruitful. All right, so today I'd like to present my topic that is on the theme of smart materials, a way forward. So let me share my presentation. Can you see that? All right.
Yeah, yes, bro.
Yes.
We can see
Yes,
you.
yes, we can see, Prof.
Thank you very much. All right, as you know that today I'd like to present something on smart materials, the prospects of conducting materials under the smart materials. Now, this topic I have chosen because this one, I love it very much. I have been working on this conducting polymers for a long time since my PhD. And it has got a lot of applications, in fact, in science and technology. So today, I'll try to share some of them. All right, so smart materials, materials of the future that we can term as it is. Okay. So it's time to be smart. Very true that we need to be smart in order to cope with that modern world, right? To be smart, S stands for significant, as for example, like this, that we can define smart as S, significant, M, measurable, A, appropriate, R, result-oriented, and T, time-oriented. If we can meet all these, hopefully we can come up with smart materials. So smart or intelligent materials are materials that have to respond to stimuli and environmental changes and to activate their functions according to these changes. The stimuli like temperature, pressure, electric flow, magnetic flow, light, mechanical, etc. can originate internally or externally. So a lot of applications, in fact, we have this in our everyday life under the heading of smart materials. So it can be found in everywhere, in fact, in aircrafts, orthopedic surgery, dental braces, robotics, reducing vibration of helicopter blades, smart fabrics, sporting goods, smart glass, and a lot of smart materials that, in fact, we have. So we have to focus to our abilities, whatever we can in this science and technology, that would be our contribution. Now, if we classify these smart materials, it can be classified as piezoelectric materials, electrorestrictive materials, magnetorestrictive materials, rheological materials, thermoresponsive materials, electrochromic materials, fullerenes, biomimetic materials, smartphone, and smart polymers. Now, I'll talk about this smart polymer, a material of wonder, in fact. A lot of applications we can find out from these smart polymers. And here we'll talk about conducting polymer. It's a smart polymer, meaning that it has got a lot of applications. Whatever we find it in terms of polymeric materials, it's one of them. So conducting polymers are polymers with metallic and semiconductor characteristics. it's not fully your conductor. It's in the semiconducting range, the conductivity falls. And this semiconducting range is good enough to have many applications in light emitting diodes, in capacitors, in sensors, in various applications, in batteries, in fuel cell, solar cell. A lot of applications actually can come up with this small your conductivity in this semiconducting range. It may not be that full conductors like copper, right? So conducting polymers, or more precisely, intrinsically conducting polymers, are polymers that conduct electricity, that is considered to be intermediate between semiconductors and metals. So conducting polymers are generally not thermoplastics. That is, they are not thermoflammable, but like insulating polymers, they are organic materials. The examples are polyaniline, polypropylol, polythiophene, polyacetylene, polycarbazole, and a lot of polymers. A lot of advantages, in fact, we have. That's why we go for this conducting polymers to evaluate its potentiality. The advantages of using conducting polymers are that they are of lightweight, inexpensive, and easily processable. So these three main things actually sorry, make us very much enthusiastic to explore in this area, in this conducting polymers. A lot of opportunities are there to play with these conducting polymers. And taking this advantage that it can be easily processed, it's not really tough. Easily can be easily processed. I'll discuss about that. That is your chemical synthesis and electrochemical synthesis. And apart from that, it has got many other advantages. If it is lightweight, it's a great advantage. In fact, it's flexible. We can flexible make it any shape, right? It can be, used for various applications that I'll discuss in details, some of the things. So organic electronics, it's another name we can suggest. That is conducting polymer. As the name suggests that it will conduct electricity. So that's why this organic material can be used in electronic devices. Or we can say as polymer electronics is a branch of electronics dealing with conductive polymer. So whatever the name we call it as conductive or conducting actually refers to the same thing. So conductive polymers are lighter, more flexible, and less expensive than inorganic conductors. There are many advantages. So this makes them a desirable alternative in many applications in electronic devices. Historically, organic materials or plastics were viewed as insulators, like polyethylene. Is it a conductor? No. We cannot find conductivity in polyethylene. It's an insulator. But if we talk about polypyrrole, polythiophene, polyaniline, polycarbazole, all these have got some electricity that can be used upon applications, meaning that if we connect this one in the appropriate devices, we observe the electricity, right? So these are not insulators, right? So with these applications are commonly found in inactive packaging, coatings, containers, toys, clothing, and so on. All these comes from these plastics. However, these plastics just mentioned that can be turned into conductive upon doping. We'll see that research on the electrical behavior of organic materials commenced in 1960s. The announcement of conductive polymers in the late 1970s and consecutive semiconductors and photoemission polymers in the 1980s gave a new impulse to the activity in the field of organic electronics. Polyacetylene was one of the first polymers reported to be capable of conducting electricity. And it was discovered that oxidative doping with iodine causes the conductivity to increase by 12 folds of magnitude, for which the Nobel Prize was awarded in chemistry in 2000, in the year 2000. The history goes like this, that at the beginning of 1970s, Professor Hideki Shirakawa at Tokyo Institute of Technology, TIT, Japan, was studying the polymerization of acetylene into plastics by using Ziegler-Natta catalyst. It's the normal way of preparation. It was going just as usual. However, a foreign student in Shirakawa's group tried to synthesize polyacetylene in the natural way. Nothing wrong, very good way it was going. Suddenly, one accident occurred. Just we can say a scientific accident, and that led to this conducting polymer to emerge. A beautifully lustrous silver-colored film, rather than the black powder, was obtained with a great surprise. Shirakawa found that the foreign student, whose Japanese was not quite up to the mark, added 1,000 times more catalyst to a reaction than he should have. As for example, he was asked to take some milligrams. He took grams. So it was quite high amount of catalyst that changed the whole polymer into something interesting and really astonishing at the time. Shirakawa was stimulated by the accidental discovery and later found that the molecular structure of the resulting polyacetylene was affected by the reaction temperature. For instance, the silvery film was trans polyacetylene, whereas copper-colored film was almost pure cis polyacetylene. So in another part of the world, Professor Alan G. McDermid from New Zealand and Professor of Chemistry and Professor Alan J. Hager, Professor of Physics at the University of Pennsylvania, Philadelphia, USA, were studying the first metal-like inorganic polymer, sulfur nitride. In 1975, Professor McDermid visited TIT, Tokyo Institute of Technology, Japan, and gave a talk on the sulfur nitride. After his lecture, McDermid met Professor Shirakawa at a coffee break and showed that a sample of golden silver nitride produced by Shirakawa, and then consequently, Shirakawa also showed McDermid a sample of silvery acetylene, acetylene, polyacetylene. Right. Now, the beautiful silvery film caught the eyes of McDermid, and he immediately invited Shirakawa to the University of Pennsylvania, since McDermid and Alan J. Hager had found previously that the conductivity of sulfur nitride could be increased 10 times after adding bromine to the golden sulfur nitride material, which is called doping. They decided to add some bromine to silvery acetylene films to see what happens. Miracle took place on November 23rd, 1976. At that time, Shirakawa worked with Dr. C.K. Chiang, a postdoctoral fellow under Professor Alan J. Hager, for measuring the electrical conductivity of polyacetylene by a 4-probe method. To their surprise, the conductivity of polyacetylene increased remarkably. This day was marked as the first time observed the doping effect in conducting polymers. In the summer of 1977, Professor Alan J. Hager, Professor McDermid, and Professor Shirakawa co-published their discovery in the article entitled Synthesis of Electrically Conducting Organic Polymers, Halogen Derivatives of Polyacetylene in the Journal of Chemical Society, Chemical Communications. With the discovery of highly conductive polyacetylene doped with iodine, a new field of conducting polymers, which is also called synthetic metals, has emerged. In 2000, in the year 2000, Professor Alan G. McDermid, Professor Alan J. Hager, and Professor Hideki Shirakawa received the Nobel Prize in Chemistry for their accidentally discovered conductive polymer. And that was a great journey. In fact, from that, we are having this conducting polymer to play with the various parameters to come up with various applications. So they were the pioneers in providing this material to us. So conducting polymer, in fact, has the conductivity in the range of semiconducting range. So here is the range. We can see that it's in between metals and insulators. So what makes the materials conductive? That's the simple question comes. And it's a very obvious question. How can we make a plastic conductive? These three simple carbon compounds are diamond, graphite, and polyacetylene. They are all these made of carbon. Now, this hydrocarbon, that is polyacetylene, graphite, or diamond, all these are carbon compounds. So they can be regarded as 3, 2, and 1-dimensional forms of carbon materials. Diamond, which contains only pi bonds, is an insulator, and its highly symmetry gives its isotropic properties. Graphite and acetylene both have mobile pi electrons and are, when doped, highly anisotropic metallic conductors. That's why graphite, being a carbon material, can be used as an a material that can conduct electricity. And that's why we use this one as an electrode. However, diamond cannot be used as an electrode because of this configuration of this structure. Now, plastics are polymers, molecules that form long chains repeating themselves. That is polymers. All we know that monomers, they join together to form long chain of polymers. Polymers having this repeating units of monomers. So in becoming electrically conductive, a polymer has to imitate a metal, that is, its electrons need to be free to move and not bound to its atoms. So polyacetylene is the simplest possible conjugated polymer. Conjugated polymer meaning that alternate way, having double bond, single bond, double bond, single bond. So it is obtained by polymerization of acetylene. The first condition for this is that polymer consists of alternating single and double bonds. These are known as conjugated double bonds, alternating way. In conjugation, the bonds between the carbon atoms are alternately single and double bond. So every bond contains a localized sigma bond, which forms a strong chemical bond. In addition, every double bond also contains a less strongly localized pi electric bonds, which is weaker. So the second condition is that the plastic has to be distributed either by removing electrons from it, that is oxidation, removal of electrons, or oxidation, right? So inserting them into reduction, meaning that the electrons, if it comes back, it's that reduction occurs. So this process is known as doping. So there are two types of doping, P doping, we call it, or N doping. Sorry. So oxidation with halogen, we have this P doping, and reduction with alkali metals, we call it N doping. If we look at it, that you find that a number is missing, right? 1, 2, 3, 4, then 8, blank, 5, 12, 6, 7, 11, 13, 9, 10, 15, 14, right? The game offers a simple model of a doped polymer. The pieces cannot move unless there is at least one empty or hole, right? If there is a hole, then it's possible that the numbers can be shifted. So in the polymer, each piece is an electron that jumps to a hole vacated by another. So this creates a movement along the molecule and electrical current. So the halogen doping transforms polyacetylene to a good conductor. Oxidation with iodine causes the electrons to be jerked out of the polymers, leaving holes in the form of positive charges that can move along the chain. So if we look at it, if we see that the iodine molecules attracts an electron from the polyacetylene chain and becomes iodide 3 ion. The polyacetylene molecule, now positively charged, is termed as a radical cation or polaron. The lonely electron of the double bond formed, which an electron was removed with an electron and was removed, can move easily. As a consequence, the double bond successively moves along the molecule. The positive charge, on the other hand, is fixed by electrostatic attraction to the iodine ion, and which does not move so easily. As mentioned before, that this way we develop conductivity in our conducting polymers, and there are many variables, many parameters responsible for producing conductivity in conducting polymers. Many factors are involved. If we choose a solvent, it has an effect. If we choose the temperature, preparation temperature, it has an effect. If we choose the reaction time, if we choose the oxidant, if we choose the mole ratio of this monomer to oxidants, all these vary the conductivity. The time we prepare the polymer, suppose for half an hour, it will have a conductivity different from if it is produced by taking 3 hours, right? So all these are factors to improve the conductivity in conducting polymers. A lot of things are there. All right. So factors that affect the conductivity can be generalized in this way, although a lot of factors are involved, a lot of things. So density of the charge carriers, their mobility, their direction, the presence of doping materials, the temperature. Apart from that, the polymer chains are arranged in a way that is very crystalline, ordered structure. It will have higher conductivity than disordered or amorphous structures, right? So this crystallinity, if we can increase better, if we can if we come up with amorphous structures, of course, the conductivity that may not be up to our expectation. So there are many things, in fact, in the preparation condition, in the synthesis techniques, we have to pay a good attention to the process parameters. Then we can come up with higher or desired conductivity that we observe, right? That we wish to produce. All right. So this is the simple way of producing conducting polymer using using a potential stat in electrochemical technique. So there is another technique known as chemical technique. Chemical technique meaning that we do not need any potential stat. Simply, if we choose any monomer in a beaker, if we add oxidant in a solvent, in a suppose suitable solvent, and then if we allow, it will form conducting polymer. So easy. But it's not that easy to produce of desired quality. It can be produced. Well, conducting polymer is produced, but if it cannot be used as a material in electronic devices, then it's of no use, because it cannot be used in any practical applications. However, the material is produced, true. But what's for? If it cannot be applied, right? So we have to be very cautious in preparing the conducting polymers in terms of conductivity, in terms of its morphology, in terms of its shape, size, so many things, and porosity, whatever it is, whatever we need for any particular application. And all these come from synthesis condition. It's very, very important that synthesis condition should be paid utmost attention. Really, it matters a lot. Even if we rotate that whole beaker, it will come up with a product that is different from the static way if we prepare. So here we notice the role of shaking, the role of ultrasonication. So these have got tremendous effect or good effect when we just simply change the process condition. Ultrasonication will bring very fine powder, fine material, which is in the form of nano. So nano conducting polymers can be produced by ultrasonication, right? So we have many techniques here: ultrasonic rod, we have ultrasonic bath, and many other sophisticated your instruments available for producing these nano materials without adding any foreign materials. It's just simply coming from the preparation technique, not from adding any third component. So many things, in fact, we can do that. So if we come back to this synthetic preparation, synthesis of conducting polymer by electrochemical technique, we need one potentiostat. Well, it should be connected to 3 different electrodes. So one electrode, if we see that, it's that working electrode. Another one is that counter electrode. Another one is that reference electrode. So these 3 electrodes will be required in producing this conducting polymer. It's the simple way of preparing. However, in this cell, we take the monomer, the electrolyte, and of course in the solvent, proper solvent, that which solvent we wish to prepare. If it is water, fine, can be. If it is methanol, organic solvent, can be. If it is acetone, acetonitrile, can be. Methanol or organic solvent, whatever it is. All right. So now this is the technique of preparing conducting polymer by chemical technique just mentioned. It's very easy. Anybody can do. Anybody can do in any laboratory. If we have any glass beaker, of course we do have, right? Beakers are very common apparatus. In every lab we have. If it is not, even we take any like this, any bottle, anywhere, anything that is your capable of, holding the chemicals. And if it doesn't react with that, yes, it's fine. We can produce in a cup, right, of tea. When we take tea, right, this cup can be used also, no problem. So apparatus, in fact, is not at all any problem. It can be any glassware. All right. So we take what we take inside. We take monomer, we take the oxidant. Of course, in any solvent. Sorry. Okay. Now, the normal way of preparation is that polypyrrole, as for example, that typical way of preparation is that previously it can be used in various mole ratios of monomer to oxidant. We can take it 1:3, 1:1, 1:2, and then we check the conductivity, and we can find out the effect of this mole ratio between the mole ratio of monomer to oxidant. All right, so time is also another factor. Can be 3 hours, can be 5 hours, well, to produce very thick powdery form. If it is produced by 1 hour, well, it will be thin product, meaning that not very too much product. So it affects also. The conductivity also matters. All right. So in this simple way of preparation, if we look at it, as for example, and this is the example. Suppose 0.33 gram of pyrrole monomer was added to 30 ml of distilled water, and it was mixed. I mean, can be stirred first. Sorry. To have your thorough mixing. After that, we add the desired amount of oxidant. As for example, in this case, 1.35 gram of ferric chloride hexahydrate to this mixture of monomer and water already there. And then we keep it for some time, and we find that black polymeric powder forms. So it's that very simple way of preparation. Now this is the final product. It's very black in color. This is, I'm talking about polypyrrole. It can be other monomers that can be used. As for example, aniline, it will form polyaniline with different color, may not be that black, but greenish. Black towards black, but it's greenish and then black towards black, like that something. So polyaniline, polythiophene, polycarbazole, these are the conducting polymers. Often we find that this polypyrrole is quite good or acceptable in electronic devices. Sometimes, yes, polyacetylene is also considered as that very good material for its application in electronic devices. However, and here comes the scope of doing research. If we do with polypyrrole, if we do with polyaniline, if we do with polycarbazole, if we do with polypyrrole, polyaniline, polythiophene, polycarbazole, so many things actually. If we do all these, meaning that our properties will not be same. Different in terms of conductivity, in terms of its morphology, in terms of its pore size, volume, pore volume, many things actually will be different. So based on the monomers, based on the oxidants, based on the solvent used, based on the reaction temperature, based on the timing, based on the shaking condition or that static condition, and when it's prepared under shaking, right, it will affect. So many things, in fact, we can do that one. We have a lot of room, means the room for improvement of its properties to our desired material to produce something of our interest. Now, conducting polymers, as mentioned, can be used in a lot of applications actually. Is really a long list. It has got a long list. So anti-static substances for photographic film, it can be used as corrosion inhibitors, can be used in capacitors, and can be used as anti-static coating, electromagnetic shielding for computers or for television or any other devices that electromagnetic wave comes and it's shielded. It will not have the interference with the device. As for example, we are using computers. Sometimes we find that electromagnetic wave can come and disturbs. If any motorcycle goes by, then previously, long time ago, we used to see that our television screen used to vibrate. Meaning that wave was coming to this computer, to this electronic device of this supposed television or computer, and where we found that it's really affecting the screen, is vibrating, some noise, it means your disturbance. So here is that application of this electromagnetic shielding material, and this conducting polymer can be used. Very good thing, because this is flexible. We can bend it, we can make it some various shapes. But if it is made of your iron, meaning they are very metal, it's difficult to make shape, to bend, to have flexibility. It cannot be, right? So here it enjoys the advantages. So a second generation of conducting polymers have been developed. These have industrial uses like transistors, light emitting diodes, lasers used in flat televisions, solar cells, and also the your fuel cell membrane, and the electrodes. All these can be used. A lot of applications, as I'm telling you time and again, it's really very interesting material, that is smart materials or smart polymers, we can say. So if we look at it, that shielding material for this computer screen against electromagnetic waves, and it's used in solar cell, can be used in light emitting diodes, a lot of things. So if we look at that, for these electronic applications, we need conductivity. For conductance, free electrons are needed. Conjugated polymers are semiconductor materials, while doped polymers are conductors. So the conductivity of conductive polymers decreases with falling temperature, in contrast to the conductivities of typical metals like silver. So today, conductive plastics are being developed for many uses. You see that it's flexible. If you look at it, that somebody is holding the conducting polymer and it can be bent, right? Without breaking, it will not break. If it breaks, meaning that mechanically is not strong. We need to pay attention to its mechanical strength improvement. That means, how can we improve the mechanical properties? Here is another room of work, right? A room of opportunity that we can do that. That means your mechanical properties improvement, because the product what we have produced is not mechanically strong. So it can be mechanically strong. At the same time, the conductivity should not decrease. That's another point to see. In order to increase the mechanical properties, we have to ensure that the conductivity does not fall. If it falls, then how? How will it be used as a conducting polymer for this particular application? We have come up with good mechanical properties. However, we failed to retain the conductivity. So we have to make the balance of that. So here's that smart windows. Now, electromagnetic shielding, I just mentioned. It can be used in rechargeable batteries, TV or computer screen, flexible electronics, sensors and biosensors. Very interesting thing, in fact. These conducting polymers can be used in biosensors, in sensors. light emitting diodes, drug delivery, a lot of applications. So in wastewater treatment, yes, it can be used as adsorbents apart from its conductivity. We are not concerned about this conductivity for using as adsorbents. Adsorbents is that the formation of this conducting polymer in such a way that it can absorb heavy metals, dyes effectively, right? So here, conductivity is not that important or is not concerned. However, the material is conducting polymer, but it's used in a different function. As for example, that your suppose holder of this pen like this. If we put pens, it will be pen holder. If we put spoons, it will be spoon holders, right? But this is a holder. So at the same this way, there is our polymers, conducting polymer. When we talk about this conductivity, it can be used in electronic devices. When we do not use this conductivity, rather other applications based on this structure, it can be used in different applications, like here it is in this case adsorbents. All right, so it can be used in biosensors as just mentioned. So today I'll share you one interesting thing, that is molecularly imprinted polymer or MIP based biosensor, molecularly imprinted polymer. In our group, we have come up with one development of one biosensor based on this molecularly imprinted polymer or MIP, that is used for DNA detection of pork. Pork DNA detection, that is in terms of halal food products, it's very useful. That the product is free from pork or not, it can detect, right? So in order to do that, we have prepared this molecularly imprinted polymer. So we need to know what is molecularly imprinted polymer. If we look at the terms used here, that is imprinted polymer molecularly, meaning that something we prepare first. We prepare the polymer with the template or the analyte molecules together with this monomer oxidant and the analyte together. Later, if we look at the picture, you'll see that all these are assembled. After that, we selectively take out the template or the analyte and make a cavity in that polymer. Done, our work is done. That is, a molecularly imprinted polymer electrode has been prepared. Now, anywhere, if we find the template molecule or the analyte molecule available in any solution, it will come back to this previously created this your cavity exactly. If any molecules comes with different shapes, it will not enter. Like lock and key. In the lock, we have a specific key to open. Is it that any key can open any lock? No, that is master key. That's different. I'm not talking about that. But any lock, if it is locked, we need to find a specific key to open. Meaning that the key is designed in such a way that it will only be applicable to open the lock. Same way, here it is that the analyte molecule, as for example, glucose, we are producing, as for example, glucose biosensor. So we are taking glucose molecules along with this monomer and the oxidant to produce the polymer with glucose, right? After that, we selectively take out glucose out. Then, so glucose molecule will have this cavity inside this polymer. Anywhere If we find glucose molecules again in the solution, it will come back to fit in that previously left area. No other material will be able to fit in because it will be larger or smaller. But this one will have the exact structure to come in and fit. So this is the principle of molecularly imprinted polymer, whereby we take the analyte molecule together with the polymer. Later, we selectively take out of the analyte and make a cavity. This cavity, when it's remaining there, it's used as a sensor for that particular analyte. Anywhere it's available, it will come and then fit to that original position, and no other things can come and fit. So this is that beauty of this, meaning that molecular imprinted polymer is so precise, so accurate, so good. So in this way, we produce biosensors for pork detection, that is your DNA of the pork. So we took these research objectives in hand. That is, we synthesized MIP, molecular imprinted polymer, using polypyrrole, titanium dioxide, and polypyrrole iron oxide as nanocomposite by electrochemical technique. Later, we have characterized with usual characterization technique like FTIR for this structure, FESEM for the morphology, HRTEM for again the morphology, the EDX, that whether the materials have got this your metals or not available, XRD also the crystallinity, BET for the surface area, and the electrochemical characterizations. All these were done by the cyclic voltammetry and electrochemical impedance spectroscopy, EIS. So this study also done to have the sensing performance of the prepared MIP for detecting swine DNA by electrochemical technique. So this is the step that was followed for preparing the electrode MIP, molecular imprinted polymer. First of all, we took all these here in this cell, electrochemical cell, to their pyrrole monomer, pyrrole with titanium dioxide in one preparation, in another preparation, pyrrole with iron oxide, right? And then with that electrolyte, in this case, paratoluene sulfonate was used. However, there are a lot of electrolytes that we can use. After that, we had this connection with this potentiostat. Now, working electrode was used, ITO glass. ITO glass, indium tin oxide glass electrode was used as the working electrode. It can be FTO, fluorinated tin oxide, or can be platinum electrode, can be gold electrode, can be, right? On the top of it, it will be produced. The polymer will be produced as a polymeric film. All right, so the reference electrode can be mercury chloride, silver chloride, and that auxiliary electrode that can be used as graphite rod or your gold can be. All right, so this way we produced your polypyrrole with DNA together. Later, we had the task of removing DNA to make it MIP, molecularly imprinted polymer. To this end, what we did, we have chosen selective solvent. In this case, ethanol with acetic acid with that mole volume ratio, that is 9:1 for 15 minutes of treating with this mixture. And later, we found that the template came out. That means the DNA came out from this, and there was a test for that. Previously, with DNA, we have this FTIR spectrum, and removing that one, we have another spectrum. Besides that, we have also test for this, whether DNA has been fully recovered, removed or not. There are so many techniques actually to confirm. Now, so this way that MIP was produced. Later, it was used for taking that pure, means your real sample, and we found that the pork your, that means the DNA came to this position again to giving us the peak, meaning that it's working. And if we took any other substance, any other meat like your chicken or your buffalo, it didn't match, right? Okay, all right. So it's duplicated. Okay. So conducting polymers have emerged as smart polymers with lot of promises in the field of sensors, biosensors, energy storage devices, light emitting diodes, electromagnetic interference shielding, and many other applications. In our laboratory, previously, I have worked on this MIP, your electromagnetic interference shielding. Also, I had the opportunity to work on biosensor, that is glucose biosensor, normal. And later, I have focused on DNA biosensor. Apart from that, I have also focused on this, your treating as adsorbents. That means conducting polymer for absorbing heavy metals and dyes from wastewater. Right. So there was some efforts that Alhamdulillah I put into. Anyway, my research interest, in fact, is to go ahead with that, with the preparation of conducting polymer for different applications in sensors, in EMI applications, or in environmental pollution problem, to use it as adsorbents. So apart from the electrical uses, electronic devices, it can be also used for addressing the environmental pollution problem as adsorbents for heavy metals and dyes from wastewater. So my research is now is on this as well. So I'm focusing on this. At the same time, also looking for other applications, like trying to focus something on cancer cell treatment. Later, I'll try to find out that how we can address this issue. All right, with this, I thank you very much. And here are the list of bibliographic search. All right, so there are the references. All right, thank you very much.
Okay. Thank you very much, Professor Dr. Ikram, for such an insightful and thought-provoking presentation. We truly appreciate the depth of knowledge you share with us today. Now I'd like to open the floor for question. If there's anything that wasn't entirely clear, or if you'd like to delve deeper into any particular topic, this is your opportunity to ask. Please don't hesitate to raise your hand or type your question in the chat. We encourage you to seek clarification on anything that might be unclear, as this is a great chance to gain further insight directly from our esteemed speaker. We are here to ensure that everyone leaves this session with a solid understanding. So please feel free to ask your question. Boleh, Bu Rina? Dari student.
Also, I'll be glad to receive any inquiries through my email or WhatsApp. Any communication will be good for me also, no problem. I'll be glad to hear any questions or anything to discuss. If there is no question now, I'm really very happy to receive any comments or any questions through my email or through WhatsApp. Any communication will do.
Udah. Oke. Hello, good morning, Professor Habibin.
Good morning.
I really appreciate for your presentations, and I'd like to know about the molecularly impacted polymer (MIP). So we just started to conduct research about MIP, but we have difficult to we have template monomer and then polymerization, and we would to make GeoMIP, MIP, so we have to remove the template. But when we remove the template, how to choose the solvent in order to remove easily? Because we need more volume to remove the template.
All right. So
Thank you
please
very much.
follow. If you see the guide, if you wish to take any guideline, it's first we have to look at the established research, the literature. In the literature, in our case, we have found that ethanol and acetone together with this proportion of 9:1 volume ratio. Suppose 9 ml is to 1 ml. So this way, that a mixture, and we tried, and then it could be removed. So in your research, you try to find the proper solvent with various mole ratios and check ethanol and acetone. If you mix it with 9:1 mole ratio, see that, or in the literature, what is suggested, you try to follow that one in your area. So this is that something trial basis we need to find out. In fact, there is no formula of such, because my student tried many times, to collect, could not. Later we found that, oh, this, if we make a mixture, then it was successful. Alhamdulillah. So you can try with various solvents with mixing, right? So better to check a lot of solvents. A lot of solvents we have, like methanol, ethanol, propanol, butanol, or acetone, acetonitrile, right? Or DMSO, anything. So which solvent will be appropriate to give this answer? It will be easier if we look at the literature that previously people have used what solvents, and then how was the performance, the efficiency or the performance. And to this, please follow very good journals. Do not follow ordinary journals like any ordinary journals. As for example, Bangladesh, your Chemical Society, or this Journal of Poland, Journal of China. I do not recommend this type of easy journals, or the not very good quality journals should not be followed, because there are so many misleading information available in that. Right? We will be simply misled that we are going to follow, and finally is not coming up with that. So try to find out very good journal, very high quality journal, like your suppose impact factor very high in your area, right? Very good American Chemical Society, published by American Chemical Society, as for example, or the European Chemical, any good journal from Europe, from America. So this type of journals actually need to be followed instead of African Journal of Technology, Bangladesh Journal of Science and Technology, as for example, or any other journal that is of not good quality, meaning that we are not getting good information from that. This is my message. It's not that I'm just disrespecting or dishonoring them. In fact, not that. We want to learn in a proper way, in an effective way. Correct. So that's why it's required to say that we should consult very good journals, right? If this follow good journals, do not follow ordinary journals. Sometimes they are misleading. That's what I'm telling. Really misleading. And if we follow, then finally do not come up with any good result. And they do not write in details. So if you come across with this any problem, but by following any particular journal, directly you write it to the author, the corresponding author, that we are trying to find out. However, your method, could you please elaborate us in details in your email? You just ask them to give the explanation, to give the details of their procedure. Sometimes the procedures are not in details in the journals. So that's the problem we face. So for that case, it's better to communicate directly with the authors.
Thank you, Professor. Sorry, previously I have not introduced my name. My name is Rinawati. I'm from Chemistry Department, also same with Dr. Sony.
Okay.
Thank you for
Okay.
your information, and
Okay.
I'm very happy if I can contact you. I will contact you for the
Okay,
further.
sure. Most welcome. I'll be glad. Alhamdulillah, I'll be very much honored, definitely.
Thank you, Professor.
Anybody can
And I'll
ask?
be very much happy to receive any your corresponding anything that I most welcome. Any communication is you are highly welcome to communicate whatever the help I can give. Of course, I'll do that. If not, at least I can suggest, as for example, that you contact this person or this experts. So this is the case. This is the thing. So you are most welcome. Anytime you can approach me. I'll be more than glad.
Thank you, Professor.
Okay, thank you, Professor Ikram. Anyone want to ask? Maybe I want to ask Prof. Ikram about MIP. Could you please explain how MIP improve the sensitivity and selectivity of the biosensor? And what the current challenges in integrating MIP with biosensor technology?
I cannot hear you properly. It's coming very fade way. Not clearly or loud. I request to make it louder, please.
Okay. I would like to ask about MIP and the application in biosensor. As you said that it can applied in the biosensor for pork DNA. How to improve the sensitivity and selectivity of biosensor?
It was actually according to the literature, what we found is that good, satisfactory in the sensitivity that whatever the student analyzed, it fell in that satisfactory range, meaning that quite successful in producing the polymer as well as in the application side in terms of its sensitivity, accuracy, and interference effect. All these were satisfactory level. But there are many things to improve, that we need to work further on that. We need to work for the stability of that polymer, that electrode, whatever we have produced, right? Some product has been produced. So this needs to be tested for its longevity, which means how long we can use it, meaning that after preparation, after 1 hour, after 1 month, can it be used or not, right? So this type of thing we need to study further. This is that something we can say preliminary results that we came up, but a lot more things to do, a far away to go, right? Meaning that we need to go far. So a lot of things needs to be tested as well, including the your in terms of this product quality that can be used in future, right? With that quality, right? Because quality falls with the passing of time. That is called stability. So it's need to be studied in details, or good attention should be paid that for this stability. Suppose if the product comes to the market, the time it has been produced, and after that, after 6 months, if it expires, meaning that the product is no longer be used, then we need to check for that, the stability, that it can be used for 1 year, 2 years, right? Otherwise, the product cannot be used. So in conducting polymer, what we have found is that it's stability. This is the very important thing to address. That is the stability problem. We need to find out the solution, that is how we can improve the stability, keeping the performance same or good, right? Performance should not fall, but the stability will increase from 2 weeks to some more weeks, like that. So this type of results, actually, we need to study a lot, some more, that's the case.
Okay, thank you. We
But this form MIP, in fact, we can do for many things like cholesterol, like your glucose, like dopamine, like your many other biological things that is used for diagnosis of our many things of our diagnosis of various things. So these are the things like cholesterol. We need to find out that cholesterol level is high or not. We need to find out the diabetes, that is your glucose level is high or low, or what is that. So these are the sensors for our practical use that we can come up with, that dopamine, to use that dopamine. So all these MIP can help, in fact, better than non-MIP. Biosensors without MIP and biosensors with MIP, the difference is that MIP sounds to be more precise, more accurate than normal biosensors. That is the case.
Okay, thank you, Professor. There is one question from the participants, from Muhammad Shukri. Good morning, Professor. I'm Muhammad Shukri. I'm listening about the application of molecular system in drug delivery. My question, what are the main challenges in developing smart polymer materials that can adapt to changes in the temperature or pH in the body?
That in terms, may I request you to repeat that one?
You can read in the chat box.
MIP for
What are the main challenges in developing smart polymer materials that
okay.
can adapt to changes in temperature or pH in the body?
Oh, okay. So actually, it needs to be studied based on the literature. What's now available for this? First, we need to chalk out first. We need to find out that what are the materials used for this and how to improve. First, we need to look at the demand of the things. As for example, the oxidation of glucose is very, very important. So we need to find out that glucose oxidation will be good in what environment or what process conditions, right? If it is required that the surface area needs to be very high, then we address to that how to increase the surface area. If we find that the porosity needs to be changed or this, so what are the associated problems in that particular research, we need to find out first. Later, we need to think how we can overcome. As for example, the conductivity is required for measuring these some of the things, right? For some of the applications. Now our target will be how we can improve the conductivity without deterioration upon time, right? So these are the things. In fact, we need to find out a particular research with conducting polymer, for conducting polymer-based research from the literature and look at that. But what are the problems associated with that? First, we need to identify. Later, how we can overcome. So this is the case. This is the way thing. So many things, among many things, if we talk about these challenges, I'd like to say that conducting polymer is suffering from a stability problem. Mechanical strength is also another problem. Mechanical, it should be strong to have any application. Your environmentally, it should be very stable because in the atmosphere, we have oxygen. And when oxygen is there, it's oxidized, already oxidized. So how can it be used for further oxidation? Because it's already oxidized up in the environment, right? Because we have got oxygen in the environment. So is it that always we need to keep it in a oxygen-free environment? That means it's a barrier or it's a challenge. How to improve that one, that is the stability, when we can use it in the normal atmosphere. Otherwise, we need to keep it some desiccator, in the desiccator or anywhere that is your moisture-free or your oxygen-free container or anywhere. So this preservation will be required. So this is a barrier, right? That is the case. Yeah. So stability problem is that main problem. What we find is that this is conducting polymer is not very stable after 3 months of preparation. As for example, then the conductivity falls drastically, very low. Comes very low because of the environment. Oxygen is available. Yeah. Any
Okay.
other questions?
Yeah. Please.
Okay, good morning, Prof. Ikra.
Good morning. Yeah.
Yeah, I'm Ilim, the head of the postgraduate study of chemistry. I want to know about our research. our research is about polymer for corrosion inhibitor. Maybe maybe you can give us some suggestion. We synthesize the low molecular weight of polymer for phenylpyridine oligomer with the molecular weight about 200 to 900.
Okay.
And we applicate to this is the product is applied to the corrosion inhibitor. So we want to know how to produce the single polymer. I mean, maybe we need to know the polymer with the molecular weight about 500, for example. So it is very difficult to get the single. Maybe we all know about the polymer. So maybe you can give a suggestion about how to separate the range of the polymer, because the product it's very good for the corrosion inhibitor for mild steel in the CO2 corrosion, and the mechanism is the chemisorption. So maybe it is interesting to explore the research. Maybe can you give us the suggestion about the how to separate the polymer, maybe in the journal?
Okay. So
can
how
you
to-
get the point?
Okay. So actually, I haven't focused on this corrosion inhibitor as the conducting polymer. However, you can if it is that molecular weight, if we are talking about the molecular weight, you need to increase the molecular weight or just
No. This is in the experience we get the result. The lower molecular weight is better than the high molecular weight. So
lower
maybe
molecular weight is better than higher molecular weight.
yes.
Okay.
Yes.
Okay. So
So
meaning that you have to look at the synthesis condition, preparation condition to make it very thin molecular weight, meaning that molecular weight will be lower.
yes.
Okay. In order to do that molecular weight lower, do you find that if it is made in nano form, it works?
Not yet. Not yet.
Okay. Okay. So you can first sonicate this one with ultrasonication. If I'm not telling that.
Yes. Okay. But
Okay.
we haven't done yet
Okay.
with the sonication.
Okay. So if you do sonication, meaning that the molecules will be in fine form, very thin form, right? So when it's polymerized, it will come up with this, very fine polymers. Maybe that can be of low molecular weight. I'm not sure, but based on the timing, based on the mole ratio of the product of the reactants, focus on the mole ratio of the reactants. Also, you can sonicate and make it very thin, very fine powder, fine materials. That means the reactants, so that after polymerization, it will not form any gigantic polymer.
Okay.
Any large molecules of polymers need to be hindered, need to be obstacled, right? So that it will not form a very gigantic, very polymer, right? So to do that, you can it may help if you focus on this sonication, and so that the particles will be fine particles, and upon polymerization, maybe it's of low molecular weight, and the timing, if you reduce the timing, make it very thin, very low your concentration.
Okay.
Low
Yeah.
concentration low. Concentration of the monomer and the reactants, all these are low, sonicated, timing is less. All these, you look at it, how it can be, improved or not.
Okay. Thank you, Prof.
Okay.
Okay. Maybe I can discuss with you for
Okay,
next
no
time.
problem.
Maybe for
Yeah,
yeah
please
more
send me
information.
the journal papers, the references, so that
Yep.
we can focus in a better way that they have done it, they have come up with this low molecular weight, and using this technique, using these process conditions,
Yeah.
these are the
Mm.
things.
Okay. Thank you very much, Prof.
Okay.
Ikram. Nice
You're
presentation.
welcome.
Nice presentation.
All right, thank you very much.
Pak Sony.
Thank you, Professor Ikram, for your very interesting discussion. And if there is no question, so we come to the end of today's insightful and enriching webinar. I would like to extend. Yeah. Oh, masih ada. Oh, sorry. There is one question in chat box. Maybe you can read. Oh, enggak. Saya tadi ada keluar. Maybe you can read in the chat box, Professor. Okay, I read the question, Professor.
Yeah, please.
This is
Yeah.
from Dian Rifani Mutia. Good morning, Professor. My name is Dian. I have question about removal template for MIP. Based on your presentation, you have explained 15 minutes to remove template.
So it depends. Okay, so meaning that actually, understand. So we have to do it in a trial and error basis, because it may not be 15 minutes. For our case, maybe 15 minutes, but it can be 20 minutes, 30 minutes, based on your materials and the solvent, the mole ratio. You can change the mole ratio as well. Suppose here we have used 9:1. You can use 10:1 or very close, like your 10:1 is 1. Another one is suppose 5:1. So this type of various mole ratios of both the things, and then your timing also, 10 minutes, 15 minutes, 30 minutes. It's very important to extract. So if it requires 30 minutes, we have to accept if the results are satisfactory. If the results are not satisfactory, then 15 minutes, 30 minutes, all the same. So results must be satisfactory. For that case, if we compromise, if we need to compromise with timing from 15 minutes to 30 minutes, let it be. Still, we have good extraction. That is very, very important to ensure that extraction is appropriate and that complete. In order to do that, timing is one, the mole ratio of that solvent is another factor. Different solvents can be the another factors. Not only ethanol, can be others like your, well, methanol can be tested, propanol, butanol, this also can be tested, because research is doing something away from people have done, right? what people have done, if we are doing the same thing, meaning that we are doing experiments, not research. Research is that something we need to do what people have not done it, right? To dig into something, to go in details. Yeah. Okay, another question I have noticed that I am Ishukri, listening to a publication, okay, drug delivery. My question is, what are the main challenges in developing smart polymer materials that can adapt to changes in temperature or pH in our body? Well, we have to look at the pH sensor and the temperature sensor. For this, conducting polymers applied for temperature sensor or pH sensor should be digged into it details, and we see that what are the polymers used for pH sensor and used for temperature sensor, because a lot of materials in polymeric family can be used, can be polypyrrole, can be composites of polypyrrole, can be polyaniline, can be polythiophene, can be polycarbazole, as I mentioned. A lot of polymers are there. So in the literature, which polymers have been focused, we should check that one, and we can make the improvement in terms of making it composites with different things. Even it can be polypyrrole, polyaniline together. Can be. If it is polyaniline alone and polypyrrole alone, why not we just combine and check that combined effect it can be realized or not? Can follow? Yeah.
Thank you, Professor Ikram. I think we are reached to the end of the webinar. I would like to thank Professor Dr. Ikram Mahmud for your sharing invaluable knowledge and expertise with us. Your presentation has certainly broadened our understanding and sparked meaningful discussion. So before we close, on behalf of the chemistry study program, we would like to express our sincere gratitude and present with an e-certificate as a token of our appreciation. This is the certificate.
All right. All right, thank you very much.
This certificate is presented to Professor Dr. Habibun Nabi Muhammad Ikramul Mahmud as a speaker in general lecture on smart materials, a way forward, held by Graduate Study Program, Department of Chemistry, Faculty, Mathematics and Natural Science on September 11, 2024. Signed by Dean of Faculty, Doctor in Engineering, Heri Satria, BSc MSc. Thank you,
Thank
Professor,
you very much.
for your time.
Most
And I would
welcome.
also like to thank each and every one of you for your active participation. Your engagement and thoughtful question have made this event a success. It's all inspiring to see such a diverse group of professionals come together to exchange ideas and learn from one another. As we wrap up, let's carry forward the knowledge we have gained today and apply it to our respective fields. Once again, thank you for being a part of this webinar.
Yeah.
We hope to see you at our future events.
Inshallah.
Thank you, Professor.
Inshallah.
Maybe in the
so
future
nice
we
to
can
have with you.
Collaborate.
I'm really fortunate, Alhamdulillah. I'm really fortunate to be here with you in Lampung University, Faculty of Science and Mathematics, right? And really, it's a good opportunity to exchange views among the researchers. That if we can improve, go ahead with the research, why not? We should do. That's the case. If we love research, we should go ahead. This much. Right.
Okay. With that, I officially close today's webinar. Have a wonderful day. Thank you, Professor.
Thank you very much. All right. Okay. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Yeah.
So I
Okay.
wrap up, eh?
I will give the time to the MC.
Okay, thank you for our best speaker
All
for
right.
today, Professor, and thank you for
Most welcome.
Mr. Sony. For the next is we will have a documentation for all the participants on the Zoom meeting. Please open the camera.
Mhm.
Okay, for the first slide, 1, 2, and 3. Okay, for the second slide, 1, 2, 3. Okay, thank you so much. And
Welcome.
by the completion of the entire agenda, General Lecture Smart Materials A Way Forward is declared to close. Let's close this event by saying Alhamdulillah.
Thank you
I
very
am
much.
Anurvalitas Niani as a Master of Ceremony. Apologize if there are some words that was pleasing to the audience. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you.
Thank you, Professor.
Okay, welcome.
Thank you.
Saya wrap up, eh?
Terima kasih.
Terima kasih, sama-sama.
Kapan-kapan berkunjung ke Universitas Lampung, Prof.
Okay. You are most welcome to visit us. Huh?
Iya,
You are highly welcome.
oke. Insya Allah.
Inshallah. Come to chemistry department. We'll have chit chat. We will have, Malay foods.
Iya.
All
Okay,
right.
thank you very much for nice presentation, Prof.
All right. Thank you so much.
Hmm.
Thank you very much.
Okay.
Okay.
We-
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Oke. Sudah, itu pada diambil-ambil fotonya.